Okay, so to solve these problems, these related rates problems, now that we've kind of looked at what we need to talk about, what we're going to do is we're going to go through an example. So let's say we had this example, a hot air balloon rising straight up from a level field that you were carving pumpkins on is 400 feet from where you are. And that's talking about from the launch point of the balloon. At the moment the balloon is 300 feet off the ground, the balloon is rising at 20 feet per second. How fast is the distance between you and the balloon changing at that instant? So a couple of things to kind of take note of. Number one, there are no equations whatsoever in this problem. In fact, we only have 3 pieces of information and we're being asked to find a 4th. So what we do is we take some steps that help us solve these problems. So step number 1 every single time is we want to draw a picture of what is going on in the situation. So in this case, here you are on the field. Here's your little pumpkin carving knife right there. The balloon is rising up in the air, so here's my balloon rising up in the air. And that doesn't look very good either, but there's my hot air balloon. And here is like the launch pad that it launches from. Now, there's my picture. What you should do once you draw a picture is you should kind of say, okay, are things being measured? Are we talking about lengths or distances? And in this case, we're talking about 3 different distances. We're talking about the distance here, and then down here. So all 3 of those are different distances that are being referenced in this particular picture. Step number 2, once we've drawn our picture, we need to label everything that is in the problem with a variable that has been referenced at all. Whether or not you know how long it is, we're going to call all these things a variable. So I'm going to call that side A, because that's a length, this side B, and this side C. Once we label all 3 sides, what we're going to do is we are going to come up with an equation that relates all 3 of those sides together, or however many variables there are in the problem together. In this case, because we've got 3 different sides of a right triangle that have been formed, we get a squared plus b squared is equal to c squared. And that is a fairly important step. A couple of things to note about that is, first of all, you can definitely say that it is a squared plus b squared equals c squared. You can have as many variables as you want. There's not a limit as to how many variables we can use in these equations, but we do need to come up with an equation. Now, step number 3 says right here, we are going to take the derivative with respect to time. Now, what that means in this instance is every one of these variables, A, B, and C, are all technically functions of time. I just don't know what that function is. So when I go to take the derivative of A, it's like a chain rule is being applied. Maybe I'm just making this up, but maybe A of t is t squared plus e to the t. Maybe B of t is cosine of t plus ln of t. I'm just making these up. That's not really what they are. But regardless of what they are, I would take the derivative the same way. I would bring the 2 down, leave the inside part alone, and then I would multiply that by the derivative of what is on the inside. So in this case, that would be the derivative of A with respect to time. Then I would do the same thing with the next part, and the same thing with our third function that we have over there, and that would be our equation. Now, basically what we have done is we've said, okay, for the longest time I had these functions of time that were embedded in the function that I didn't know about, but now once I take the derivative with respect to time, all of a sudden I can look at these in a more logical story problem manner when it comes to derivatives. If you remember in the first part we talked about time is a very important variable for us to be using, so we just kind of forced it into the problem, okay? So another thing that we realize once we take the derivative is because the derivative is an instantaneous rate of change, what we have done is we realize that we can now stop time at different instances and see what is happening at those different times. So in this problem, what I have is I've got A, B, and C here, and then I found dA, dt, dB, dt, and dC, dt. Well, A in this problem is the distance from you to the launch pad. B is how high up the hot air balloon is at any given time. And C is the distance between you and the hot air balloon at any given time. If we were to talk about dB dt, dB is a very small change in B, dt is a very small change in time. So that is a distance divided by time, which should sound like a velocity. dB dt then is the rate at which B is changing. In other words, how fast is the hot air balloon rising? And then dC dt is just how fast C is changing. dA dt is how fast A is changing. So all of those represent a speed as far as how fast a distance is changing at a specific time. So if I go back to my problem, I've got 2A dA dt plus 2B dB dt is equal to 2C dC dt. Then I look at this and I look at my problem and I say, okay, at the instant in question, I know that this side is 400. It's not, they might not always be 400, but at this instant it is. The balloon is 300 feet off the ground, so I know that A and B in this problem are 400 and 300. If you think about it, this distance is like a static distance. It's not getting bigger or smaller, so dA dt represents the rate of change of the line of A. It's not changing at all, so I would call that 0. And then dB dt is how fast B is changing. That would be the same as the rate at which the balloon is rising. So I would put 20 in there. Now, technically what we're looking for is the rate at which the distance between you and the balloon is changing at this instant that we are looking at. So what I really want is dC dt. Well, in order to do that, I need to know what C is, but at this instant, I can say that 300 squared plus 400 squared is equal to C squared. And with the Pythagorean theorem, we find out that C is equal to 500 at that instant. It's not always 500, but it is in this case. Then what we do is we just do a little bit of math, so I get 1000 dC dt, because we're solving for dC dt, and that's really step 5, but I'm just going to do it on this screen. 600, that is 12,000. So I divide both sides by 1,000, and I get the dC dt is equal to 12 feet per second. And that kind of makes sense in the context of this problem. If the balloon is rising at a rate of 20 feet per second, it's slowly getting away from me, but it's not doing it quick enough that it's going faster. Like that rate is not changing. So my answer would be 12 feet per second. Let's look at one more example, make sure we have it down. Okay, so air is being pumped into a spherical balloon at a rate of 5 cubic centimeters per minute. Now this cubic centimeters tells me that we are dealing with a volume. And we're dealing with the volume of a sphere. Now, the volume of a sphere is 4/3 pi r cubed. What we can do in these problems on the AP test is they will give us this formula, so you won't have to memorize volume formulas, okay, or surface area formulas. They'll give it to you if you need it. But the only time they give it to you if you need it is if you see a related rates problem. So in this case, it gives me that formula, or it would give me that formula, and I would know that I'm looking at a related rates problem automatically, talking about the volume and the radius. So there's step 1 and 2 already done for us by the AP people. Step 3 is we take the derivative of this function with respect to time. So the derivative of v is 1, but then because it's a function of time, we put dv dt. And then the derivative of 4/3 pi r cubed is 4 pi r squared, because we bring the 3 down and multiply it by 4/3. That becomes 4 pi r squared, then we put dr dt. Now we just plug in, notice we're looking for dr dt because that is the rate at which the radius is changing. So for dv dt, I'd put in 5, then I'd get 4 times pi times the radius in this case. If the diameter is 20, then the radius is 10. So I would get 4 times 10 squared. So then I would have 5 is equal to 10 squared is 100 times 4 is 400. So I would have 400 pi dr dt. And then I would just divide by 400 pi. And I would find that dr dt is equal to 5 divided by 400 pi. Now, I know we went through those kind of quickly, and I apologize for that. I'm not going to do the last example, but if you have any questions, one thing I will talk about. On the last example, you'll have a right triangle like this, and there's a cop car going 60 miles per hour towards this intersection. Because the cop car, so here's the cop car right here. I'm not going to do the entire problem. And just if you want to know, Rollins is going 70 miles per hour. But if the cop car is going, if the car is going towards the intersection, in other words, it's making that side be smaller, then we would say that this velocity, or that, in this case, we call that side A, it would be dA dt. That would be a negative number. So I would have that be negative 60 if I put in dA dt, because it's making side A be smaller. So again, maybe try that one on your own. See if you get 70 miles per hour. You are going to use a squared plus b squared equals c squared. The difference here is none of those rates are 0 because everything's moving in tandem with it. Okay? So hopefully that makes sense. If you have any other questions about related rates, please come on in and we will get them answered.